Hello everybody, welcome into another lesson. So today we are going to talk about vector decomposition. So you're probably wondering, well, why the heck would you want to decompose a vector? Well, many applications in physics, such as finding the amount of work done, or in engineering, other areas, require you to take an original vector and decompose it into the sum of two other vectors. So you're given two vectors u and v. Everyone should be familiar with the basic vector notation by now. To decompose the vector u, you need to find the sum of two vectors w sub 1 and w sub 2, where w sub 1 is orthogonal to w sub 2. So the idea is that you're going to find vector u to be the sum of two orthogonal vectors, and also the w sub 1 vector is parallel to vector v. So to find vector w sub 1, what is called is taking the projection of vector u onto v. So you take the projection of vector u onto v, and that's given by the formula the dot product of u and v divided by the magnitude of v squared times vector v. That's vector w sub 1. And then just solving for vector w sub 2, you can get that by taking vector w sub 1 away from vector u. So we're going to do a few problems here about vector decomposition. And I will write this formula up higher so we have that. This shouldn't be a super long lesson, but I wanted to do this as a separate lesson because it's kind of a decent amount to talk about. So vector w sub 1 equals the projection of vector u onto v. That's how you would read that. It looks like it's almost backwards, like the projection of v onto u. It's actually the projection of vector u onto v, which is going to equal, of course, the dot product of vector u and v divided by the magnitude of vector v raised to the second power. So you're going to have a scalar in your parentheses times vector v. Alright, I'll even write the u equals w sub 1 plus w sub 2 up here. Alright, so let's get started here with a few examples. Now, what they're going to tell you to do is find the projection of vector u onto vector v. Then find vector u as the sum of two orthogonal vectors. Okay, so that's what we're doing here. So we're going to find the projection of vector u onto v. Once we do that, we're going to find vector u as the sum of two orthogonal vectors. So we're given that in this case vector u is equal to 3, 4, vector v is going to be equal to 8, 2. Alright, well, we can't begin to find u as the sum of two orthogonal vectors without finding the projection of vector u onto v. So let's go ahead and start working on the projection of u onto v. Well, in order to do that, we need to take the dot product of u and v. So the dot product of u and v, that's simply going to equal, then you'll take that 3 times that 8 plus that 4 times that 2. So that's going to equal 24 plus 8, which would be 32. So the dot product of u and v is 32. Now we need to find the magnitude of v. And then we need to square it. So that's going to end up being then, let's use the classic formula from the first lesson for finding a magnitude. So that's going to be the square root of your components of vector v, which in this case would be the square root of that 8 squared plus 2 squared. All that raised to the second power. That would give you the square root of 64 plus 4, all that raised to the second power, which would give you the square root of 68 raised to the second power, simply giving you that value being 68. So the magnitude of vector v raised to the second power is 68. Now that we have all that, we can find the projection of u onto v. So the projection of u onto v is going to equal 32 over 68 times vector v. Well, 32 over 68 is going to end up being 8/17 in reduced form. 8/17 times vector v, which in this case is 8 2, which would end up being 64/17 and 16/17. And the projection of u onto v is also vector w sub 1. So we found vector w sub 1 being 64/17 and 16/17. Now to find vector w sub 2, we just subtract vector w sub 1 from u. So vector w sub 2 is going to equal then that vector u, which would be that 3, 4 minus 64/17, not 67/17, 64/17, 16/17. Okay, so let's see. So vector w sub 2, so 3 minus 64/17, that's 51/17 minus 64/17. So that would be negative 13/17 for the first component of vector w sub 2. And then if we take 4 minus 16/17, so 4 in terms of 17 is 68. So 68 minus 16, that's going to end up being 52/17. And if you were to test to see if vectors v, if vector w sub 1 and vector v were parallel to each other, as we talked about with vector decomposition, you would see they are. They're both scalar multiples of each other. And then if you were to take the dot product of vectors w sub 1 and w sub 2, you would actually find that they're orthogonal. It would equal 0. So now that you found vectors w sub 1 and w sub 2, we can write vector u equal to the sum of two orthogonal vectors, w sub 1 and w sub 2, which would be 64/17, 16/17 plus -13/17 and 52/17. And if you added these together, you would get the original 3/4. So there is your vector u decomposed into two separate orthogonal vector component sums. And then your projection, which we found to be vector w sub 1, is 64/17, 16/17. So that's how you find the projection, and then that's how you would find the sum of two orthogonal vectors. Alright, so that was the first example. Now we have three more. We're going to do three more of these. So let's go ahead and do that. I don't know why I erased that notation there, but alright, so in this case, vector u is going to be 4/2. Vector v is going to be 1, -2. So the idea is, again, we're going to find vector u as the sum of two orthogonal vectors, but we need to, in order to do that, one piece of this is we have to find the projection of vector u onto v. So let's start working on the projection. We need to first start by taking the dot product of vectors u and v. So let's go ahead and do that. So that's going to then be, of course, you'll take that 4 times that 1, plus you'll end up taking 2 times that -2, which in this case is going to end up being 4 minus 4, which would be 0. So the dot product is 0, which in this case, it does not really matter what the magnitude is, because 0 divided by anything, if you want to find the magnitude of v, knock yourself out, but in the end, you're going to get 0 times vector v, which would just give you a 0 vector. So that means in this case, the projection of vector u onto v is going to end up being 0, 0. So it's, or otherwise called the zero vector. You can also call that the zero vector, which is going to be vector W sub 1. So basically, it's like vector W sub 1 is its own projection of U. In that situation, it's its own projection. And it's definitely going to be perpendicular to vector W sub 2, because W sub 2, that's going to equal that vector U, which was 4, 2, minus W sub 1, which is going to be 0, 0. Well, 4, 2 minus 0, 0 just gives you 4, 2. So we found vector W sub 2, and then we can, if you really want to, we can write vector U as the sum of vector W sub 1, which is going to be 0, 0 plus 4, 2. So there is your vector sum of two orthogonal vectors. And here is your projection. It's going to be 0, 0. And of course, if, okay, you could argue that W sub 1 is parallel to vector V in the sense that it's a zero scalar multiple of vector V, and it's definitely perpendicular to vector W sub 2 in the fact that if you take the dot product of W sub 1 and W sub 2, of course you'll get 0. So your projection is 0, 0, and then vector U can be written as vector 0, 0 plus 4, 2. Alright, I got two more of these. And these last two probably aren't going to be as nice. Alright, so vector U is 0, 3. Vector V, wow, big jump, 2, 15. Alright, so vector U is 0, 3, vector V is 2, 15. We want to take vector U, find it as the sum of two orthogonal vectors. So first we need to find vector W sub 1 by finding the projection of vector U onto V. So let's find the dot product of U and V. So the dot product of U and V, that's going to equal 0 times 2 plus 3 times 15, which would be 0 plus 45, or simply 45. So the dot product ends up being 45. Now let's find the magnitude of V, but we have to square that magnitude. So that's going to be equal to the square root of 2 squared plus 15 squared, which would end up equaling, and then of course that whole quantity squared, which would equal the square root of 4 plus 225, that quantity squared, which would equal the square root of 229, that whole square root raised to the second power, which would just give you the magnitude squared being 229. Now we just have to take our values for the dot product of U and V divided by that magnitude of vector V squared and multiply that times vector V. before I do that, I would like to see if 45 and 229 reduce. I'd really like to hope they do, because otherwise we're going to have some hideous numbers. No. Well, we're stuck with it. So basically then W sub 1 is the projection of V onto U, which is going to end up equaling that 45 over 229 times vector V, which is 2/15, which would end up giving you 90 over 229. And then we got to take 45 times 15. Which would be 675 over 229. So your W sub 1, which is the projection of V onto U, is going to end up being 90 over 229, 675 over 229. Now let's find vector W sub 2. That can be found easily by taking vector U, which is going to be 0, 3, and then subtracting vector W sub 1, which would be 90 229ths, 675 229ths. So let's take the final result. Well, the first component of vector W sub 2, that's easy. 0 minus 90 229ths, that's negative 90 229ths. And then now we need to take 3 minus 675 229ths. So let's figure out what that is. So 3 times 229, that's 687 minus 675. That would be positive 12 229ths. So there's your vector W sub 2. So now that we have both W sub 1 and W sub 2, we can write vector U to equal, let's see, W sub 1 was 90 229ths, 675 229ths. Plus we have then negative 90 229ths, 12 229ths. So all that work to get those two vector components for vector U, which are both orthogonal to each other, but you have the sum of two orthogonal vectors, which are equal to vector U. Alright, so I got one more problem, then we're done. let's see, vector u is -5, -1. Vector v is -1, 1. Alright, so vector u is -5, -1. Vector v is -1, 1. So let's go ahead now. Again, the goal is to decompose vector u into the sum of two orthogonal vectors, which we'll call w1 and w2. In order to find w1, we need to find the projection of u onto v. So let's start by finding the dot product of u and v. So the dot product of u and v, that's going to equal -5 times -1 plus that -1 times a +1. So that's going to essentially equal 5 minus 1, which would be 4. So the dot product of u and v is going to be 4. Now we need to find the magnitude of vector v raised to the second power. So the magnitude of vector v raised to the second power is going to equal the quantity of the square root of, so your components of vector v, that would be -1 raised to the second power plus 1 raised to the second power, all that raised to the second power. So that's going to equal the square root of 1 plus 1 raised to the second power, which would equal the square root of 2 raised to the second power, or just 2. So the magnitude of vector v squared is going to be 2. Now we are ready to find vector w1, which is the projection of v onto u. So vector w1 equals the projection of vector u onto v, is what I should have said. That'll be the projection of u onto v, excuse me. So that's going to equal the dot product of u and v, which was 4, over the magnitude squared, which is 2, times that vector v, or which would simply end up being 2 times your vector v, which is -1, 1. Which would give you -2, 2 for vector w1. So there's your projection of u onto v, which is vector w1. That's going to be -2, 2. Now let's go ahead and find vector w2, which again equals vector u minus vector w1, which is going to be that -5, -1 minus the -2, 2. Alright, so -5 minus -2, that's -5 plus 2, which would be -3. -1 minus 2 is -3. So vector w2 is -3, -3. Now we are ready to proceed into writing the sum of two orthogonal vectors. So vector u is going to equal that w1 plus w2. So that would end up being the sum of -2, 2 plus -3, -3. Those are both orthogonal to each other, and you have vector u as the sum of two orthogonal vectors, -2, 2 plus -3, -3. So that's it for this lesson. Next lesson we are going to get into the trigonometric form of a complex number. So we'll bring back imaginary numbers again, and we'll deal with those in the trig forms, which can sometimes actually be an easier way of dealing with them, especially when you get into multiplying and dividing them and taking them to powers. So I hope everyone has a great day. Take care.